Good morning, Year 10. So, first off, a little apology. I had a go at the homework that Miss McCall sent me last week, just because I needed to know what the questions were, and I couldn't work out how else to view the quiz without actually doing it. So I wasn't trying to be irritating, I just needed to see what the questions were. Ignore me on the scoreboard. Second thing, I've set another one for this week, which does have some similar questions. That's good. The learning forgetting curve, the shorter it is, the better between attempts. So have another go, and hopefully you should all be able to get fairly close to full marks. It's similar alkenes and alkanes ideas, but with some added cracking questions. Now, on to today's lesson. We are looking at a process called cracking. Now, cracking is very industrially important. We'll come back to that in a minute, because the first activity is a little bit of a review of alkenes and actually fraction distillation. So the first thing I'd like you to do, as usual, is as you go through the PowerPoint, making any notes and stopping when I say pause to have a go at the activities as presented. Then I'll unpause and move on to the answers. So the tasks for the start this week are, please could you, A, complete the tasks and notes on the PowerPoint, and feel free to send me a copy of that on the Show My Homework app, and I can then give you feedback on it. I would then like you to have a go at the quizzes, which I'll see if I can use the data from that to give you red, amber, green, and any feedback that's appropriate there. And there are two optional extension tasks, one slightly more geopolitical one at the end of the PowerPoint, and a slightly more practical science one in the written description of the homework on Show My Homework. So have a look at those two, decide if you want to do either of those two optional extras, and have a go at them. Send me any ideas you've got for them. That'd be marvellous. Okay, so start off is a little bit of a review. So have a look at these fractional distillation recap and see if you can put in the correct words there as appropriate. Pause. Answers. Oh, unpause and pause again because I've now got the rest of the paragraph. Okay. Last sentence done. Answers. So, in terms of the atoms in hydrocarbon molecules are held together by strong covalent bonds. However, each molecule is only attracted to the others by weak intermolecular forces. When crude oil is evaporated, the weak intermolecular forces are overcome, but the strong covalent bonds are not. Larger molecules have more intermolecular forces, so if oil condenses at higher temperatures, you could say stronger rather than more. That's an area of debate in terms of how chemists describe that. Okay, right. The context for today's lesson is this. We've got bitumen and petrol fractions, and we've got graphs showing in arbitrary units on this axis. Arbitrary units, the supply and demand of bitumen and petrol. Now, if you look at these two graphs, there's immediately a fairly obvious problem. I mean, this one's not so much of a problem. This one, more so. So, what's the problem with bitumen? Well, we get loads more of it than we actually need. I mean, bitumen is principally used for road surfacing and other tarmac type applications. It doesn't have an awful lot of uses beyond that because it doesn't burn, at least not at any sensible temperatures and conditions. And it's not particularly reactive in any way, being an alkane. It is very unreactive and it doesn't really burn very well, so that's largely useless to us. Except for putting on roads and tar and roofing felt and things like that. However, petrol, that's very useful. You notice that the supply here is rather less than the demand. So the problem this graph shows is the fact that we tend to get quite a lot of the less useful long-chain alkanes, at least more than we need of them, but we don't get quite enough of the short-chain alkanes. You could argue, of course, that actually any short-chain alkanes that we burn as a fuel is too much because burning fuels is bad, but yeah, this is more current world rather than how it ought to be. So, the solution to this problem is cracking, or at least one of the parts of the solutions is cracking. So cracking, fundamentally, is a process of taking a big hydrocarbon molecule and breaking it up into little pieces. Now, this does break the covalent bonds within the molecule between the carbon atoms to make smaller molecules. And this makes two kinds of molecules, the alkenes and the alkanes, that we looked at in detail last lesson. Now, as mentioned last time, the alkenes are particularly useful because they make polymers, and they are also very important feedstocks, making lots of other things like industrial ethanol and haloalkanes and all kinds of other things. You can add useful things to alkenes to make through addition, which we'll meet in the next topic. Now, the reason I put a recap of fractional distillation at the beginning of this PowerPoint is these two are very often confused. And for some reason, the fact that they both involve the crude oil and doing something to it that makes products has a habit of confusing people. So I like to think about this in terms of Lego. Fractional distillation is getting a box of mixed Lego and spending the next day taking all the pieces out and sorting them by size. Cracking is having sorted out a set of Lego into a certain, so let's say there are some bricks that are 2 by 10 long, and those are too big for us. We don't want to make anything out of those. We want little bricks. Taking a hacksaw and cutting those bricks up. So the first one, fractional distillation, is sorting alkanes into a group of similar things, whereas cracking is changing alkanes from big molecules into little molecules, making the Lego bricks smaller so we can do more things with them. I know the Lego analogy is silly, but I quite like the idea of sorting versus cutting, or fractional distillation versus cracking. Fractional distillation you sort, cracking you cut. Okay, just a quick recap. Here's the difference between the alkenes and the alkanes. On the left we have the alkanes, on the right we have the alkenes, and the key difference of course is the double bonds. So all the alkenes have got the presence of a carbon-carbon double bond, and that is what defines them. Notice from last week, that key thing here that's not there, there's no hydrogen there, because we've got 1, 2, 3, 4 bonds already. Okay, I'm just going to rub out the lack of a hydrogen because it actually looks a bit like I've tried to add one, which is not what I wanted to do. So there are 4 bonds, so we've got slightly wonky looking carbon there. Okay, so the double bond is the key difference. So if you're asked in the exam question, what is an alkane, what's the definition of saturated? It's only single bonds, whereas an alkene, presence of double bonds. Look for the random one that animates later. So, that double bond is key. Again, this is a recap to the last lesson, so what I'm going to get to do very quickly is, can you draw these molecules? Pause. If not, watch on and we'll do some answers. So there's ethene. Again, we've got the bonds going up and down here as a recap. So you can feel free to add the last two if you haven't done those already. Otherwise, here they are. There's the skeleton, just the carbons. There's the skeleton of carbons, and then we can put the hydrogens on. So counting the bonds. Hold on a second, it hasn't added them on until I finish the PowerPoint. So there's 3 you could work out. Do you remember, hopefully, that the formula, the general formula of alkene is CnH2n. So if I've got C5, I have H10. If I have C8, I have H16. If I have C12, I have H24. Didn't think my pen was working there. Okay, and then we can animate up the hydrogens onto the last 2 alkenes. So hopefully they were not too challenging and they remembered them fairly easily. Again, it doesn't matter which way you draw that on the top or the bottom, and it doesn't really matter if you draw these angled or not. In terms of the GCSE, they're not fussy, so here it's drawn straight up and down. That's easier when you do polymerization. Doing these at an angle just kind of looks a bit neater and is slightly closer to 3-dimensional truth, although you really ought to angle this one as well. I don't know why they're animating it. Okay, so our next little task is a blank fill, but it's going to be a little bit hard to do until we've talked about it. This is a practical that I actually do like trying to do as a class practical, although I say that with caution because it is probably the most dangerous thing you can do in the lab, and we have a few safety measures that you might be able to find out what you can do, or there are a variety of other ways. Doc Brown's has got an interesting way of doing it, which I looked at and thought, actually, that might be quite good. So I might change our methodology in school to Doc Brown's method. But equally, our little rubber tube valves work quite nicely. So if we were doing this in a lab, first of all, you'd be using a blue flame, so I don't know why the yellow one in the picture. We've got in here some mineral wool, and that's soaked in paraffin. Down here, oh, I lied, sorry. That's the catalyst. And the catalyst is, well, modern catalyst is zeolite with an aluminium silicate coating, but ours is broken ceramics, which also contains the aluminium silicates. So we use bits of broken up, literally, when kids break crucibles, we just smash up the pieces and put them into this practical to use as our catalysts. Down here we've got the mineral wool soaked in paraffin, and then that of course is a Bunsen burner flame. Now what happens is, as you heat this gently, it starts to make a vapour of paraffin, and that then passes over the catalyst, because actually you heat the catalyst principally. Let's just get rid of some of my random scribblings. So you create a vapour, and that vapour passes over the hot catalyst, and you heat this bit mostly. You occasionally heat that bit, you flick the flame to this bit to heat it, but this is where you mostly heat that arrow. So the vapours pass over there, and if the catalyst is hot enough, some of the molecules crack in contact with it, and then those vapours, those smaller chains, flow down the delivery tube and bubble up to the top here, which should be our product, which will be alkenes. Okay, have a go at filling in the blanks. We'll talk about the details of the practical for cracking in a second. There are the blanks. The alkene is heated and becomes a gas, that will be used as vaporized. The vapours pass over a hot catalyst. This causes the alkane to crack and make shorter alkenes and alkanes. I don't know why I haven't highlighted alkenes there, because it wasn't a word. Cracking is an example of thermal decomposition, because the long alkane breaks down when it's heated. So that's one of the key examples. You do get asked in Unit 1 papers, or in the first paper quite a lot, to give examples of certain practicals or certain reactions, and thermal decomposition is mentioned in the energetics topic. And thermal decomposition, when they ask for examples, one of the examples you can give is cracking. And often they'll ask, in cracking, what kind of chemical reaction is this? And what they're looking for is thermal decomposition. Okay, so you have to be able to draw or work out the formulae of, or calculate, or do it by names, the product of a cracking reaction if you're given all of the other products. So for example, let's have a look at basically what's going on. Now really, when we do these diagrams, we're talking about thermal cracking, but we'll look at the forms of cracking in a bit of detail later on. For the time being, when we talk about catalytic, the one I actually showed you in the practical form, the one I just scribbled on with a border pen in the practical, that wouldn't actually make products like this because of the way chemistry works. But this is what you have to learn as the process for cracking. So what happens in cracking is you take these large molecules, and when they are heated, and it may be in the presence of a catalyst, you end up with them breaking at some point. So in this case, I've highlighted the pink ones and the hydrogen on the end, because that'll get snapped off and then reformed, and they go to form an alkane. You're always going to make one alkane when you crack an alkane, because of the amount of hydrogen you've got. So there's our alkane. But in addition to that, I've still got 1, 2, 3, 4, 5, sorry, 1, 2, 3, 4, 5 carbons left. So I'm going to make at least one more product with a total of 5 carbons. So I've made a 5-carbon alkane, so that's pentane here. There's pentane. But I'm also, it's going pink to help highlight that. I'm also going to make a 3-carbon. Now because I've got not enough hydrogen here, this is going to have to be unsaturated. So I'm going to have to form an alkene here. So there is propene. Getting ahead of myself. That's propene. And that leaves us with 2 carbons. There they are, which I'm going to highlight in a second. When propene's finished flashing green. There they are, they're going bright pink. And those 2 carbons and 4 hydrogens. And this is the bit you would probably have to do in an exam question. They draw the first 2 for you and say, right, what's the last thing? What else is produced? So you have to go, okay, how many carbons have I got? 5 there, and 3 there. I've got an alkane there, so the next one, the last ones have to be alkenes, because I've already used up my extra hydrogen there and there. So this is going to be an alkene, and whatever this is going to be an alkene. That's got 2 carbons, therefore the alkene with 2 carbons is ethene. So draw an ethene, it's going to flash pink because why not? And there we have them. So we've got the 2 alkenes with their double bonds, and we have the alkane. So this kind of cracking will always produce one alkane and a number of alkenes. Now where the things break, where the covalent bonds break, is actually quite random. So you'll be told in the question what the products that you know are, and have to work out the missing product. Because otherwise they can't just say, what is the product? Because you can break it there, or there, or there, or there, or anywhere you like, and make a valid answer. So they have to tell you most of what's formed, and then you have to work out, say, one missing one. This does come up on the quiz later, on the Quizzes quiz. Right, I'm animating through, and I don't know why, there we go. Again, what type of reaction is this one we use to heat to break something down? Thermal, for heat, decomposition, for breaking. So, this is the bit where we get slightly more A-level. Now, your exam board doesn't go into a lot of detail here, but just enough to be annoying. So there are fundamentally two types of cracking. What we call thermal cracking, which uses heat, maybe pressure, and not a catalyst. So high temperature, high pressure is thermal cracking. The name suggests it's heat that's important. And what's called catalytic cracking, as the name suggests, that one involves a catalyst. So what I'd like to just briefly do is, rather than talking about those two general types of cracking, because there are lots of examples of each of them depending on the conditions, the exact temperature, the type of catalyst, the pressure used, whether water is included or not, your exam board, rather than sort of wanting you to learn a sort of a great deal about types of cracking, basically wants you to know two examples. And rather than being the generic thermal cracking and the generic catalytic cracking, they just want generic catalytic cracking and a specific thermal cracking called steam cracking, which, as the name suggests, involves water. So overall, if you had to define what cracking is, you have to say cracking is carried out by heating to a high temperature and become a vapour, and then passed over a hot catalyst. So the key idea is high temperature and catalyst. Now this high pressure bit, that's debatable. I wouldn't put that as either first or second marking point in a 2-mark exam question about the conditions of cracking generically. I have seen exam papers where they asked, what are the conditions required for cracking? And they wanted high temperature, and they wanted catalyst, and they did not give marks for high pressure. So if you have a 3-mark question, by all means put high pressure, but if you have a 2-mark question, high temperature and catalyst are what you're looking at. Caveat, unless they say steam cracking. So, the catalytic cracking is effectively this, but without really the pressure. The steam cracking is this, but without the catalyst. So, just quickly, catalytic cracking, this uses a high temperature and passes the vapour over a catalyst. That's the key idea. Now, you don't need to know the names of the catalysts. The aluminium silicate and zeolite. That zeolite is the word that they would actually want you to say, but they don't want you to say anything, so don't bother learning zeolite. They're very interesting things. If you want to go and have a look at the structure of an ion exchange water filter, that's made out of zeolite, and that's well worth a little bit of interest if you are feeling very, very stretchy. You want to learn some superchemistry. And steam cracking. So steam cracking, no catalyst is used. The water kind of acts a bit like one, but this is used at higher temperatures and high pressure with steam. Now once again, if you have a 2-mark question, temperatures are key, steam is key, replacing catalyst, and high pressure, whilst valid, is not what they're looking for in their marks. Okay, so that's the key thing you have to write in an exam. So high temperature, you just say high actually, high temperature, steam cracking, high temperature, and steam. Possibly pressure if they ask for a 3rd marking point, but it's very unlikely. Now, just a little bit of extra A-level slight stuff. This steam cracking, which is an example of a thermal cracking, this can actually make little alkenes in an efficient way. So actually, the one we looked at on the PowerPoint a minute ago, showing the big decane molecule being broken up into propene and ethene and pentane, was actually, that was probably done by steam cracking or one of the other thermal crackings. Whereas if you actually do catalytic cracking, what you tend to end up with are what are called aromatics and branched chain alkanes. So rather than getting nice neat little alkenes and alkanes, you tend to get quite chaotic branching alkanes and alkenes, and you make rings called, well, either cycloalkanes or if they're aromatic rings, benzene and stuff. If any of that sounds either interesting to you or scary, if it's interesting, go and Google it. If it's scary, ignore me, you don't need it. Fantastic. So, last couple of things we need to mention are testing for alkanes and alkenes, make that E really clear, and their uses. So alkenes are much more chemically reactive than alkanes. That double bond, that area of high electron density, means that they can do that addition with an electrophile. Again, not a word you need for GCSE, but you need to know that things can stick onto them, and you need to know the word addition. We can add things to these molecules. And one of the things we can add is bromine, and that's kind of useful because bromine water is a solution that has a colour, but haloalkanes don't have a colour. So what you can do is, in order to test the presence of an alkene, you add bromine water to the solution, and if it changes colour to be colourless, then you had an alkene present, because the alkene has just done addition, it's added bromine water to the double bond, and therefore you don't see the bromine anymore. So on the left here is what you'd see either before mixing, or if you mixed bromine water with an alkane, and on this side you've got the colourless version, which is what you get after mixing, or mixing bromine water with an alkene. So the key test, alkene plus bromine water gives no reaction. Sorry, alkane plus bromine water gives no reaction. Alkene plus bromine water decolorizes. So the key thing to write down, or to remember, is that alkenes cause orange bromine water to turn colourless. That's important. We don't say clear, because clear just means you can see through it, it doesn't comment on the colour. And we tend to say orange is the colour, so orange to colourless in the presence of alkenes. They will also react with other halogens, but they're not so easy to see the colour of in solution, or they're more toxic and less easy to control. Bromine water is pretty horrible stuff in its own right, but the concentrations we can use in lab at school means that we can actually show you that one. Whereas low concentrations of chlorine look pretty colourless, and low concentrations of iodine are, you can put them on your skin as an antiseptic, but it's not so useful in terms of colour as the bromine. Okay, key uses. Just because they want you to know this, and we're not going to cover it in today's lesson, the next topic is the reactions of alkenes and alcohols. So we're going to be looking at all of those in more detail and meeting the alcohols and the carboxylic acids in addition to the alkanes and the alkenes. But the key things, just on the qualitative, without understanding how they work, is that first off, alkenes make better fuels. Secondly, because they can do these chemical reactions, we use them as what are called feedstocks. And a feedstock is a chemical that I put into a process to make something else, to make other important chemicals. Industrial ethanol, and that's then used to make loads of other stuff, just as a small example. Lastly, and this one you should have met before, back in you're in year 10, back at the beginning of year 10, or even in year 9 when you did giant structures, covalent giant structures, you should have encountered the idea of a polymer. And you should have encountered the idea of an addition polymer. So alkenes are able to break their double bonds to form addition polymers. Now we will be looking at that in more detail in the next topic, because addition polymerization and the other kinds of polymerization all crop up in the next organic chemistry topic in more detail. Right. This is a relatively easy exam question, but feel free to pause and have a quick go at it. I'll tell you the answers in a second. Okay, so X, Y, and Z. Well, they're not all alkenes, and they're not all alkanes. What they all are is hydrocarbons. So all of those are hydrocarbons. What type of chemical reaction takes place when X is converted into Y and Z? Well, that's a type of chemical reaction. It doesn't ask us what to name it. The name would be cracking. That one's thermal decomposition. Components Y and Z are both useful substances. Y is unsaturated and Z is saturated. One use for Y could be making polymers, or as a feedstock to make ethanol, or just as a feedstock. It's also a good fuel. One use for Z, that's basically just a fuel. Okay, so the option on this PowerPoint for extra learning is to look at some geopolitical stuff in terms of oil supplies. But I think actually a slightly more useful thing for you to do with this, if you want to do any extra learning, would be the one that I've written in the show homework task about finding a safe lab method for doing cracking. Now, we do have a way of doing it relatively safely. There are certainly ways that we can improve it. It is pretty good, but you need a brief method for a small-scale demo or lab practical, and tell me things that are important, like how do I avoid having implosions or explosions of my glassware? How do I avoid having chemical fires if my glass breaks? So a very bare bones method, perhaps a diagram, and a fairly bare bones risk assessment, talking about the key hazards and what you could do about them. You don't need to include a risk assessment for the testing of the alkenes. Bromine water is horrible, just that'll do. That's definitely a teacher-only thing. So if you want to have a go at this one instead, feel free to do so. And it's to do with oil prices and factors that might affect oil supplies to the UK. But I think actually the one about the practical is probably a bit more interesting. Either way, I hope I haven't been too rambly. That is cracking in all its GCSE level interest. It is a very useful industrial process. You need to really remember that it is the whole breaking up of molecules rather than sorting them out. And that difference between cracking and fractional distillation is always quite heavily examined. You tend to get more 6-mark questions on the fractional distillation stuff because of the whole not breaking bonds but breaking into molecular forces thing. Means that it's quite good and quite nice to get descriptive marks out of for an exam question, but equally cracking itself can make quite good exam questions as well, because you're talking about alkenes and alkanes and sometimes their properties. So both of these could easily be a 6-mark question, and both of these are well worth being very, very clear on the process. Moving on, or rather actually, not moving on. Have a good week, enjoy yourselves. Sorry I've lost Miss McCall, at least in terms of setting work. You will hopefully be seeing her in school though. Right, have fun, take care, stay safe, bye.